Some of you wrote that. It's pretty good. So what's the under one condition that I took that as a good answer? Okay. The shear fault waves never get to the filter material. Somebody wrote that it is indeed prevents the washout of the core into the rock-till shell under rapid drawdown conditions, which is correct. So, I took some. I appreciated the artistic license that some of you exercised. If you wrote that and you wrote that stuff, I said, okay, you're right. But generally, what I was looking for, that it's a crack stopper. Explain the downstream method of constructing tailings dams, and what are its benefits and shortcomings. So basically, these questions, you have to answer each and every question in it. One, explain what's the downstream method of constructing dams, and then talk about its benefits and shortcomings. Okay, so again, you have to get it right. Downstream, upstream, center line, they're different. Some downstreams were actually upstreams and stuff. So, upstream method, you have to tell me how it's constructed using a sketch, explain, and also its benefits are basically a higher stability, it's a good foundation material, you can build in cores, you can build in drainage, whatever you want, you can build in. But of course, the amount of material required is much higher than the other two methods, and the associated cost is higher. So,
and the time?
Yeah, it takes longer. So these are the things that I want. I mean, what I see, another thing is that you guys, you have to be technical people when it comes to drawing sketches. Something that, an 8-year-old can draw. I've seen put together. And again, this is not really a criticism, it's more like I was okay with the grades and everything, it's more like for you to have a learning experience of how to do it right. Like, this is what I saw for the downstream one. So, tell me 2 things that are wrong with that one. The slope and the center. So this ain't a downstream. This is a hopefully nobody builds anything like that. Okay. I know time is of essence, you're in rush, but if you do sketch something, it has to be appropriate of the concept you're trying to. Okay, dams constructed on what type of soils are prone to liquefaction and subjected to earthquake loading? What was I looking for? So, cohesionless material that's saturated. Dry sand is not really prone to liquefaction. And in many, many, many cases, it just says sand, loose, whatever, granular material, cohesionless material. If saturated was missing, well, that's not the answer, right? It has to be saturated, sand or saturated, granular, cohesionless material, whatever you want to call sand. Okay, so again, specifics. Why is the settlement of the crest of an embankment poses a serious problem, and how can it be prevented? So, why is it a problem? Yeah, loss of freeboard, settlement, differential settlement, deformation, all sorts of things. How can you prevent it or correct it? Cambering it at the design stage. Some of you wrote that you camber it afterwards. I don't know. Correcting it, that's where the RCC dam came in and somehow raise it. Okay. Good. Homogeneous one we talked about. Excessive vegetation problematic on earthen dams. Why? And list at least 2 reasons. So what's up with excessive vegetation? Yeah. Visibility and roots, well, they grow towards the core, which is saturated or filled with water, creating perhaps potential pathways for fighting type of erosion and all that. Now we have to make sure that bunnies and other animals are not vegetation. Okay? They're animals. I've seen bunnies in here, but bunnies ain't vegetation. Okay, what is segregation and why do we need to worry about it in placing embankment materials?
Segregation is a separation of fine particles from coarser ones, and you have to worry about it because if you have segregation, it compromises wood distribution and gets the cold out of it.
So the larger grain stays on the top, lower grains go to the bottom. One of the answers I saw segregation in context of concrete. It freaked me out and kept me up all night. That's a different course. That doesn't score too much. Okay. So before I hand it out, are there any questions regarding the midterm as far as, I try to go through it in 5 minutes or 10 minutes just to, to give you an idea of what I wanted. Anybody? No. Okay. So if you still feel after going through what I expected the solution, if you still feel that you have any questions, on a separate piece of paper, write it down what it is, attach it to your midterm, and hand it back to me. I'll look at it and get back to you individually. I will not discuss it during the break or after the class or anything like that. Okay? So I'll place it. Where should I place it? Here? Okay, I'll put it down in the right.
Appelsohn, Abel, Bullock, right? Prince, Proyecto, Veronica, Manjar Telal, Kaspar Gasseni, A.M. Shanket, Mate Salim, Chini Juan, Amin Kazen, Amina Kazen. Someone else got it?
Well, that's good. So we'll look at, do appreciate that the way these are presented in pretty much in a historical order. Not only in historical order, but in an order of increasing complexity. So if we go back to the phi equals 0 method, note that the soil mass was only one large volume. Now, for some soils it might be okay, but generally you do not expect the soil mass, say at 30, 40 meter high slope to fail in one shot and collapse. So the Swedish method, attributable to its developer, the other name is, which is much more telling, the ordinary method of slices. So what are slices? What do you think of slices when you hear the word slice? So what does it mean?
Pieces like bread.
Cake, anybody? Yeah, that's what I think. So slices, which means that we subdivide the volume into pieces. Now, why would we want to do that? The number one reason is, it's pretty much up here, that the shear strength that was mobilized was basically independent of the level of stress in a soil mass. Now, if I look at this statement, can anybody explain it, why it's kind of not accurate? I'll make some space here. That's the question. Statement says that for the phi equals 0 method, the shear strength or shear strength was independent of the level of stress in the soil mass. So consider point A and point B. This would be a typical question for the second midterm. Prove it to me, the meaning of that statement. That kind of helped you out. So can anybody take a stab at it and see what's the problem with, why it says it's independent of the state of stress?
Because in the finding method, we only relied on the cohesion, it's like the Andre shear strength. So we said that the shear strength will be equal to C, whereas like you do have like the effect of the stress that will increase your shear strength.
Yeah. So phi equals 0 method, just as it says that this was 0, tan of 0 is 0. So no matter what the normal stress was, it was only the cohesion. So the big deal is basically that the normal stress across this interface at two different points, and even if I get sort of I don't even consider the lateral stress, even if I get the normal stress somehow from the overburden at that particular point, the distance here and the distance there are very different, right? So the normal stress, if it's the phi equals 0 method, phi has a volume, the normal stress varies hugely. But for the phi equals 0 method, the normal stress was not considered at all. Hence, it was uniform no matter where you were in the slope. Right? Now, generally for effective stress, the shear strength is related to the effective stress and now the full Moore Coulomb failure criteria. So that has to be considered. And the easiest way to look at it is basically if I subdivide now the slope into slices, and let's say at the center of each slice I can calculate what the shear stress or shear strength is. Of course, the more subdivisions I make, the more accurate it is. Now, there's nothing to say that these slices, they have to be vertical ones. But that's one of those advanced methods. We'll look at it briefly much later, that these slices, the interslice faces, they don't have to be vertical. Like, they could be something like this. Now, without saying too much, why would ever want to have the interslice sort of faces non-vertical? What's the benefit of that, if there is anything? There is a huge one. I want you to think about it. What do you think? Exactly. If I have this slice as vertical, right, then I'm saying that I'm assuming and I'm calculating in my equations the shear only in that direction. Whereas the most critical shear could be at some other angle. So by being able to find this angle as part of the solution that has the most critical state of shear, it gives much more information about the internal kinematics of failure. Now I consider now these not like a set of dominoes that the bottoms are locked off, but more like a set of blocks that can change size and direction and everything based on what is the actual collapse mechanism of these blocks sliding down. But these are sort of much more advanced methods than those. They add a much greater degree of complexity when it comes to formulating. Okay, but I want you to sort of appreciate. So, any thoughts about these three statements? Why phi equals 0 method is not so appropriate for anything more complicated? Now, at this point, I would like to draw your attention, unless you noticed it already, that each of these methods is developed, the formulation developed from the same principles, pretty much going through the same steps when doing the solution. I want you to recognize that, so when you're studying for it, you'll be able to, and there will be a slide towards the end comparing the methods, but when you're studying, try to figure out how things are put together, and you will realize that it's done exactly the same way. So keep that in mind, but without saying much else, let's look at briefly the setup. We have the slope, we have the failure surface. We are assuming a circular failure surface, therefore it's a circle, right? We can define it by its center or its origin, which is an x and y coordinate, and the radius, which is a distance measured from the origin to the circle that's intersecting the slope. So if I now flip back a couple of slides to that guy, even though it was the other direction, same idea. Origin, radius, failure surface. Okay? So these are circular failure surface methods. Now, we have a slice. And I'm just showing one slice, but there's another one next to it, and another one next to it, and so forth. There are n number of slices. How many? Well, it's up to you. The more, the better. Of course, the more there is, the longer it takes to calculate. Just like for the infinite slope method, to incorporate the effect of the next slice on either side, there are these interslice forces, z left and z right. Okay, these are basically reactions that are occurring on these interslice faces. Now, they have an arbitrary inclination, so if you resolve them along the interslice face, they would have a shear component in up and down direction, and they would have a normal component. But generally, they are inclined at some angle. Each slice has its width, b, which is not shown, but if I know what is the inclination of the base of the slice, which is alpha, so this angle alpha is basically the inclination of the base of the slice at that particular location, which is at the center of the slice. And if I know the width of the slice measured in a horizontal direction, I can calculate L, which is the length of the slice along the failure point. So this is where the shear is developed. This is where the shear strength is mobilized when it's needed. Just like before, there are two forces, P, which is equal to the component of W resolved perpendicular or in the normal direction to the portion of the failure plane, and T, which is in a shear direction, so it's either a force opposite if it's the strength, or a force downwards if it's basically the force caused by the stress, by the weight. Very similar to what we have here. Right, so we have the weight, we have the angle of the failure plane, T and P. They're the reaction. Of course, they're equal and opposite to W or its components because they're basically on equilibrium, static equilibrium. Everybody okay with this? So, for that particular slice, at the base of the slice, we know that now I'm using the equation that lived up there, the more Coulomb failure criteria for shear strength. So I have to know what is the cohesion on that portion, I have to know what is the normal stress, and I have to know what is the pore water pressure, if there is any. And finally, I have to know what the friction angle is effective, right? Because we generalize, we include water. So, can anybody explain what this equation is? What kind of a shear strength is this? There's a special name. That's this one. I'm asking about what's the name of that special shear strength. Yeah, it is the mobilized shear strength. Right? This is the part of the capacity that I need to mobilize in order to counter the driving shear stress. Okay? Similar to before, forces P and T are the normal stress times the length. What's missing here? Yeah, the depth, right? The thickness. 1 meter, we're doing 2D analysis. That's an implied 1 meter thickness. And same with T, the shear stress or strength, whichever way you want to call it, is multiplied to get into a force by an area. So this L times 1 meter is the area at the base where it's acting. So it's basically this length times 1 meter into the stream. That strip, that's where the forces are acting. Okay? Now, if I plug in this equation with the factor of safety into that equation, I would be able to come up with, and now is this stress or strength? Strength. Right? This is strength, right? If it involves the capacity. And now these are forces, so just like multiplying by L, this is now a cohesive force, and this is a normal force and a hydrostatic pressure force. That's due to the pore water pressure. Why is it negative? Why is that negative? Fundamental soil mechanics.
Because total stress equals shear stress plus water pressure.
Total stress is equal to effective stress. Yeah. Okay, so it goes back to the effective stress concept. Now, at this point, I underline it because it's fairly important that there are only very few methods that are complete in a sense that they satisfy, remember these are equilibrium methods, that they satisfy all equilibria for that particular situation. So, for 2D problem, planar problems, how many equations of equilibrium do you have? 3, which is
Some of the x is 0, some of the y is 0, and some of the y is 0.
yeah. So the two forces and the moment equilibrium. Okay. Now we have to make a small sort of expansion to all this, as we will see. That for a slope that's subdivided into slices, I'm just going to do 3, there has to be a global force equilibrium, I don't know, call it G. So this is X, G, Y. So this is for all the slices with all their forces, all the external force, whatever you can have, this ideally should be maintained, right? The whole slope is, forces should be 0, moment should be 0. And also, we have to have, ideally, per slice, there has to be a force local x equilibrium, a force local y equilibrium, and a moment local equilibrium, right? Because each slice ideally should be in equilibrium, right? It all makes sense. 3 equations of equilibrium, the whole slope should be in equilibrium, but each individual slice on its own should be in equilibrium. Make sense?
One slice is not in equilibrium. Is that like the whole slice?
It has to be ideally in equilibrium. There should be no net force or moment on it that's unbalanced. Right? The method is limit equilibrium. Now, the sad reality is that only very few methods guarantee both global and local equilibrium of all quantities. Most of them don't. So most of the slope stability methods are actually incomplete. They do not satisfy all equilibrium conditions. So, Swedish method has an assumption that the resultant of interslice forces Z is parallel to the base of a slice. So if you look at this figure, the line here, the line of action of these two is parallel to locally to the base. So how does it look like if I have multiple slices? Get my favorite piece of chalk. Well, it should be for this one, it should be, in that direction. For this one, it should be in that, it should be in that direction, parallel to this. For this one, it should be in that direction. For the last one, it should be in this direction. It's a huge assumption. Huge. Does it reflect reality? Not really. But the Swedish fellow who had the ordinary method of slices decided that this is a reasonable assumption. So, if I assume that condition, then I can now break the forces, now the actual weight. So this is the capacity, right, or the strength, and now I'm working on the driving forces or stresses. So if I make that assumption, I can break up the weight of a slice, and we're still talking about one single slice. I said nothing about the whole slope. So I can break down the weight into 2 components, one normal to the base of the slice and one parallel. So P and I guess T is somewhere else. What you can do with it. Now, another thing that Swedish method says, it only says that overall moment equilibrium about the origin is satisfied. So it says that this is satisfied, this line. Says absolutely nothing about the rest. Yeah. So if I do this, then summation over all slices, okay? Summation over all slices, so let's look at this one first. T, sum of the T's times R, which means that some of these forces, so for if there's another slice, so I can just sketch it here, get another little sketch. So let's call it T1, T2, T3, T4. So T1, T2, T3, T4 multiply by R, and you have to appreciate that R is constant, right? It's a circle. So all these force times moment arm creates the actual overall moment that's trying to keep the slope up, right? Sum of the T times R's. These are some of the shear strength forces. Everybody sees that? This is what's keeping things up. What's trying to destabilize it is sum of the weight times R times sine alpha. If P is equal to W cos alpha, then we have to appreciate that the component of the weight downwards parallel to the base is W times sine alpha, right? Those are the forces. If I have a component of a weight, then along the base, I have this component of it. Okay, that's the angle between the horizontal, and that's the angle, so this would be 90 minus the angle, or the sine of whatever the base angle is. And note that the base angle varies. Always measure, whatever from the horizontal. So, if I have all these components applied at the base, I'm going to draw yet another figure, so you can clearly see. If in the future, I'm not going to draw all these figures, just right now. So I have now all these weights bearing down. So they have at the center of the base a component that's in this direction. These are the forces that try to fail the slope. Right? They're still applied at these locations, and each of those is a distance r from the origin. So the sum of those that's rotating this way, trying to destabilize these. Okay? So the two gotta be equal because I'm claiming overall moment equilibrium. So this is basically the equilibrium equation, and now we just plug in what we have. Another big assumption is that the interslice forces remain internal and the net moment is zero. So what does this statement say? What's the implication from this figure? Okay, another typical midterm question. Explain to me what the statement is that Swedish method, the ordinary slices method, it claims that the internal interslice forces are internal and their net moment is zero. So what does that mean? And of course, screw.
Internal, or
Yeah. So note that it says that they're parallel to the base. So the momentum, they should be equal and opposite. That's what this statement says, number one. Number two, the line of action and the distance perpendicular to the origin, which is, by the way, not r, some number, doesn't really matter. But because they're the same and they go through the same line, if I take a moment, ZL times whatever that moment arm is, going this way, and CR times the same moment arm going that way, they cancel. Again, it's a huge assumption. But that's what the method says. You'll see later that other methods have completely different assumptions. So everybody okay with what this statement is? So basically, they cancel out. You don't really use them in the equation. So having said that, now I just plug things into the equation. We can simplify that R occurs on both sides, so I can simply cancel it out. So we have W sine alpha, sum of that, and T, I make the substitution. I basically put the form from here into there. And now I can solve for the factor of safety and substitute for P, which is W cos alpha from this. And there you have it. The overall moment equilibrium is satisfied, so the factor of safety for moment, or the ordinary method of slices, is basically the shear strength divided by the shear strength as a force divided by the other force that causes failure. So see, R is completely out of the equation. And that's pretty much it for the method. So, does it say anything about the sum of fx and sum of fy for the overall slope? No, it says absolutely nothing. So, keep in mind that you get a factor of safety. This is for global moment equilibrium. That's all that you get. You don't get any proof or assurance that there is an equilibrium maintained as far as forces are concerned in any of the directions. Now, if again, I'm not going to ask you to calculate these things because there is, it's a lengthy calculation and there's not too much point. But if I were to ask you, just tell me briefly the steps, looking at this equation, tell me briefly the steps that you would take to set up the equation. I just want you to grow an appreciation of the solution process. Look at it for a moment. Let's see. Give you 2 minutes. Think about it and then we talk. 2 minutes are up. What do you need to calculate the factor of safety? The steps that you need to accomplish in order to calculate it. The equation. Look at the equation. What do you need? Okay, so number one, you would need to calculate the weight of each slice, which is basically calculating the area of each slice, multiplied by the unit weight of the soil, and you get the weight of each slice. Okay, fine. What else do you need?
We need a radius and an origin.
Next slide, I need the origin and radius. Which you need that before to get the slices. What else we need? I'll look at the equation. You're about to solve it. Okay, we need the soil properties, cohesion, friction, whatever it is. What else? Yeah, definitely where the water pressure. Yes, so at the center of each of these. Calculate U. Of course, I'm not talking about that yet, how to get U, but you have to get the volume forward. What else? Okay, how do we get alpha? The reason I'm dragging this and trying to pull it out of you, because at the end it's a typical question. I give you a method and I want you to write down all the steps and how to do it. What he's telling us is that basically you find the inclination, like you know these 2 points because you know where the slices intersect, and you can find the angle using these 2 points as a line segment. Right? What else do you need? Last one. Once we know these 2 points, we can easily calculate the length of it. So if you calculate all that for each and every slice, the easiest way to do it is in Excel. You set it up, you sum it up, and there it is. So if I ask you to do 3 slices or 30 slices, other than you crying all of it, it's the same procedure. Right? There's no magic. You know the geometry, you cut it up into slices, you get these intersection points, you get to it in Excel or whatever. So, any questions about the ordinary method of slices? Okay, let's go one complication further. Bishop's simplified method. This is, or rather this was and still is to some extent, the bread and butter of slope stability analysis in software or in geotechnical offices. If you know nothing else about slope stability, this is the method that's pretty much ubiquitous. It's everywhere. Everybody uses it or abuses it, depending. It's for you to judge at the end of the course. But this is the method that widely used. briefly explain it in my undergraduate soil mechanics class, and it has certainly a place in a graduate course and, like I said, in the consulting environment. Now, again, in a consulting environment, you have to know its sort of shortcomings, right? So let's look at the setup and the first major assumption. It assumes that the interslice forces are horizontal. So if I now look at the interslice forces, I have EL and ER, left and right, and I have XL and XR. So what's the volume of XR? Look what the ghost is showing you here. Right? The cursor jumping back and forth. Normal? Look at the statement and tell me what's XL and XR are. The ghost is getting impatient here, moving the cursor. Yeah, of course. Assume that interslice forces are horizontal, so only EL and ER exist. XL and XR assumed to be zero. No shear between the slices. How good of an assumption that is? Well, not really good. But this is what Bishop says. If you compare it now to this setup, this one, the interslice forces are not broken rather into two components. They're just showing the resultant. And they said the resultant is sort of collinear and parallel to the base. So Bishop goes a little bit further and he says, well, you know, they don't have to be collinear, right? They're applied at different points. So he relaxes. So he allows a moment between the interslice forces. Now, I said that, so I want you to tell me, what do I mean that Bishop's method allows a net moment between the interslice forces based on this figure? Yeah. So if you notice that if I take moments with the interslice forces, the line of action of this force is at different distance than a line of action of that force. So there is this much difference between the two. So that could be a net moment. The previous method said no, there shouldn't be a net moment. But Bishop says that these forces are horizontal and EL is equal, that XL and XR are equal to 0. Other than that, if you look at it, pretty much everything is the same. It's the same origin, it's the same inclination, width and length, the same weight of a slice. Forces P and P as the reaction forces are still present. So when again you're building up the method, you'll see that the same steps are applied, but with different assumptions leading to different methods that are derived. So, same stuff, more Coulomb failure criterion. I write up the shear strength. I write up the mobilized version of it. I say that the normal force is the normal force is the normal stress times the area that it's acting on, which implied 1 meter. The shear force is the shear stress or strength, depending on which version you're looking at, times the area that's applied, which is the base length of the base times 1 meter. I plug in now this equation into that equation to come up with this. And I also plug in, I expand rather the effective stress as total minus forward pressure. So, resolve vertically, and the equality. You tell me, which one of these 6 is that statement? There are 6 possibilities. Let's go with column A, and let's go with column B. That line, resolve vertically, and the equality sign, is it A 1, 2, 3 or B 1, 2, 3? Yeah, it is the per slice equilibrium in the vertical direction. So you gotta know these things to interpret them. I'm not spelling all of them out. That let's say sum of forces in the vertical direction per slice are equal to 0. No, I say that if I resolve it vertically, and I say that whatever per slice is going to be equal, meaning it's in equilibrium in y direction. So for one slice, we have, going back to the figure, we have a component of T and a component of P, the reactions resolved in a vertical direction, so it's T times sine of the angle plus P times cosine of the angle equals vertical direction. We have W and we have XR going up and X left going down. So if W is positive, then it's their difference. So it's minus XR, it's going up, and XL is positive because it's going down in the same direction as W. Okay, so this is the local or per slice vertical force equilibrium. Now we said that the assumption is that the interslice forces are horizontal. That implies that XR and XL are equal to 0. So then this part of the equation goes away. And then now I can substitute pretty much everything in. So let's see what we have. For the previous equation, we have cosines and sines. For T, I would be able to put in this equation, right? I can put that in, and for P, I can put this one in if I really want it. So note that this is now the equation that's from here. But remember, P is pulled out, right? And has to be divided by another trig factor. So, if you do not believe in me for homework, work with this equation, set it up, plug in everything, shuffle it around a little bit, and you will arrive into this form. Okay, I just want you to sort of look at it briefly. W is from here, right? So I take it's basically W minus T sine alpha divided by cos alpha. That's what I'm working with to get P. So we have now this for T, dividing it again, moving things around a little bit, and so forth. You end up with this equation. Now, Bishop says that now I have overall moment equilibrium. So, what equation is this for the 6 that we have? Okay, so we have global or overall moment equilibrium. So far, Bishop is B2 and A3 satisfied. That's how it's going. So overall moment equilibrium, we have pretty much the same what we had earlier. W times sine alpha, which is, if we go back, W times sine alpha, it is going to be the component of the base that's parallel to the base, W times sine alpha, going this way, clockwise, minus or equal to whatever we have going now counterclockwise. So W sine alpha times R, force times momentum, has to be equal to T times R. These are at the base, T times R for each slice, and we're summing it up all the way. And then, just like we did before, I can solve for the factor of safety if I wanted to, and I would be ending up with this situation. But keep in mind that there's a little bit of a complication. If I put, now imagine that I put P into that, so all this I can put into that equation. Look at this last statement. So that causes a little bit of an issue. Can everybody see what the issue is? I want everybody to see what the problem is, even if you read the last statement.
Factor of safety.
I am solving for the factor of safety, but P contains the factor of safety. So I want to find the factor of safety. In order to find it, I need to know the factor of safety. That's usually not good. So how do we deal with that? Well, we resort to an iterative solution. How does an iterative solution work?
Do a seed value, find the new factor safety,
Yeah.
and then you start merging.
Well, so if I just look at it now as an operator that I'm doing, if I assume a factor of safety, let's call it fx1, what would be a good assumption for factor of safety starting if I have no clue what the factor of safety is? 1 is a good number, it either fails or it doesn't. So 1. So you put fs equals to 1, you put that into the equation to find P, you put P into the lower equation, you calculate a new factor of safety. Then what do?
Use the average. So you have 1, and let's say you think 3.
So first you have to make a decision. Yeah. If they are same or their difference or absolute difference is below a threshold, so let's say if let's say mathematics or computer science. So if the difference, the absolute value of the difference between the two factors of safety is less than a threshold value, then I say, okay, converge. If it's not, then I take fs2, put it in to calculate p, and then I calculate fs3. I go through the check again, and I do this couple of times, and it's been proven that it takes about 5-6 iterations to converge to, I guess, 3 or 4 decimal digits. So now you do realize that all of a sudden your computation grew. You have to repeat solving this equation 3, 4, 5 times in order to get the factor of safety. Everybody sees that? So compare that to something like this, where you just bang, you set it up once and off it goes. Now luckily, you don't have to recalculate weights and stuff like that because the geometry does not change, just the forces. Any questions? Now, before I start, let's see, it's a good time to stop. Yeah, let's have a break for 10, whatever minutes and continue. Okay, so there. One thing that you have to appreciate so far, even though there's an iterative procedure to solve this, the Bishop's method, what is that you get at the end? That's the big question. Okay, you get a number. What's that number for? Okay, but let me flip back to this figure. What's that factor of safety for? What does it represent?
Capacity of working.
That's absolutely correct. But, it's a factor of safety for what?
For the particular section.
Exactly. It is the factor of safety for a particular location of a failure surface, specified by its origin x, y, and radius r. Now, I sketched this little thingy. I have a slope. I want you to tell me the factor of safety. And we went through this mental exercise earlier in the course, but it's important, so let's get back to it. So, if I ask you for the second midterm, this is the slope, I can give you the material properties, I'll give you the material properties, I give you C and I and gamma, I can even give you the slope's height, I can give you the inclination angle here, whatever theta doesn't matter. I want you to tell me what's the factor of safety. What kind of a task did I give you? So what are you going to do if I give you this task? Oh, unfortunately for the midterm, you can't.
But in Excel?
No, we ask you where's the circle.
No, there is no circle. It's part of the question. What's the factor of safety of that slope? Like I showed you, there's no little sign here at the top of the slope saying that, the factor of safety, or rather the surface starts here and another one here showing that it ends here. There isn't. So when we go back to the question again, I'll give you the material properties, I'll give you the slope geometry. What's the factor of safety of this slope? No Excel, no computer program, we do it the old-fashioned style. Age of your, pardon? That's a very good question. How long do you want it to be?
Well, we can use the infinite slope or the Swedish circle or the Bishop's method. Can we use any method?
You tell me, is the infinite slope appropriate?
It solves for factor of safety and normal for
Yeah, it solves for a factor of safety.
But you know, one is
I wouldn't, but is it appropriate for the situation? Okay.
this loop for
we should calculate it for 3 different surfaces and take them
Why 3? Where are those 3? No, she asked, I said, how long do you want the midterm to be?
Can it be like a
Okay, you can take it home. When are you going to come back? If ever. The whole semester enough?
Depends how fast you are.
So trying to make you think, to realize something. We talked about it earlier, but I'm going to the extremes. I give you the angle of friction.
Comparing with the angle of the theta.
Okay, and
Like, let's say the angle of friction is 45 and the angle of the mountain is 30, I would divide the two angles. That's what I would do, like, really fast. Because I know that if the angle of theta is bigger,
remember, this whole course is about, well, half of it is about slope stability. And I don't think any of the methods includes adding the two angles and divide by 2 to get a factor of
no,
safety.
I'm dividing them.
Okay, dividing. Okay. So, going back to my initial question, given the material properties in a slope geometry, I want the factor of safety. Look at it as an engineer in a context. Now you have a tool set of couple of methods. 3 methods. Let's not use the infinite slope. What's the biggest hurdle?
All the time required to compute all the possible factors.
You have no clue where defect or failure surface is with the minimum factor of safety. We talked about this earlier, of course, right? So the biggest thing is, well, now you can use Bishop's method, you can use the Swedish method, phi equals 0 if it's appropriate. But, like he says, select 3 and take the minimum. Yeah, which 3? And why those 3?
I think as a rule of thumb, you can use the height of the wall and then go horizontally how high it's right there. I've heard that one.
Okay. Anything is better than nothing. Any other thoughts? And this is all hypothetical. All I want is you thinking and saying something, so I remember when it comes to the final grading that you were thinking, as opposed to sitting and not you are thinking, but being too shy. Okay. So the question is again, given the slope geometry, material properties, what's the minimum factor of safety for the slope? So we got why? Could be 0.8. Yeah. So that's the minimum. So we realize that even though you can use Bishop's Swedish method, phi equals 0, whatever, you still have to have, because all of those are for a particular failure surface. And now we also realize at this point there's an infinite number. Right? I can spend an infinite amount of time of drawing infinite number of failure surfaces and don't even get to calculate. Okay, so the big question is, when we get here, that I need to find a minimum factor of safety for the slope. That's what the question is. I mean, if you're in a business of doing this, people approach you with a sketch of the slope or whatever. Okay, what's the minimum factor of safety for the slope? They don't give you the failure surface or anything like that. That's, it's part of the problem to find the failure surface. So, minimum factor of safety and of course the corresponding failure surface. And keep in mind this is the simplest, almost the simplest case. X, Y, and R. The center of a circle and radius. But the big question is how many circles, where do you put it? I want the critical one. I want the minimum. Bless you. So that's the huge question. You can have a wonderful method, any of these methods, but it's not going to help you to find the critical, the minimum. So, simple methods, brute force, as opposed to like having an infinite points and infinite radii. Well, and again, I explained this briefly, I believe, earlier, that we do it in a systematic fashion, that we explore this space of the center of a circle and also the radii, and the simplest one would be to adopt a grid search, which we define an area of plausible centers or origins of circles, right? Even picking an origin like this grid area is a sort of a problem on its own, right? Because I can have an infinite number of locations, and I can have a center of a circle that's here that gives me failure surfaces like that, which are not that big. So even defining a region in which the centers of circles are is not a simple problem, and there are guidelines as far as within programs are. There are automated ways of doing it, of looking at the extent of a slope and narrowing down all the potential plausible centers that there could be, at least in the region that's usually a rectangle or a square or something like that, because not every circle intersects the slope, and even the ones that intersect do not form a failure surface that can actually fail, like those two on the top. They have no incentive as they are to fail. Okay, so the first task is trying to define, to explore the space where I would have the centers of circles. Everybody with me? Now, if I know where the centers are, then from each of those centers, let's pick this lower right corner, how many radii can I pick to form failure surfaces? I have xy now. How many r's I can have? Yeah, I can still have an infinite number of radii. Now, are we going to have infinite number of radii? We're not going to have, so we pick a sweet number like 100 or 1,000, whatever. Okay, so I keep this point, and then I generate 1,000 or 100 circles based on 1,000 different radii. Okay, and I analyze each of those. So for one point here, I have, let's say 100. I have 100 problems to solve, and let's say I'm using Bishop's method. And even itself, this one, once I set it up, it needs iterations. So I have to solve, and then I'm just going to start tallying it up here. So let's say I'm using Bishop's method. So I have, let's say, 5 iterations to calculate the factor of safety for a failure surface, right? So it converges. We discussed it before the break, okay? So I'm saying that I'm going to have, for each of these grid points, I'm going to pick 100 circles. So I have to do this 100 times, right? So what do I do once I have 100 factors of safety? Yeah, I keep the minimum, right? That's what I'm interested in. After all, the question is, what is the minimum factor of safety? Now, how many of these centers of the circle should I have? Theoretically, you can have an infinite. Let's say, let's have 10 in that direction, 10 in the other direction. So we have 100 of these sides, which is a fairly coarse, but, let's stick with it. Not that good at math, so if anybody wants to multiply it out, how much is that? A big number. Like 1, 2, 3, big numbers. Okay, so I would need to solve this equation if using Bishop's simplified, whatever that number is. Pardon?
Million times. 5 million times.
Yeah, so let's say 5 million. Is it 5 million? I don't know. Not that good. So let's say 5 million. So 5 million times I would need to calculate the factor of safety for a fairly coarse grid of values. So I have 100 values of factor of safety. We'll see in a moment what are we going to do with it. But generally, software, so if it's 5, generally software has 100 for the radii, but these go, say, 200 by 200, something like that. More than 5 million. So, how long you gonna take to come back if you take this midterm home? How many years ago from now, summer? Quite a few, probably. I'm just trying to again illustrate the issue. That even though the equations themselves could be complicated, there's just simply no point of doing hand calculations in this course, or in this time and age. Okay. Again, I mentioned it last time. How long do you think the computer, your laptop, takes to do? And we agreed last time, I believe. Anybody remembers? If not, then let's, guess. Pardon?
Not even a minute.
Not even a minute. Anybody else?
1 second.
1 second. Anybody else?
It depends.
The latest, let's say the latest one with an i9 processor, although some of these can be run on like multi-core machines. So let's say an i9 with 6 cores.
0.00 1 second.
It takes a second or two to calculate your 5 million or whatever the other number is. Okay, so a couple of summers from now, or a second or two later. Of course, a couple of summers from now, how many mistakes will there be in that hand calculation? After a couple of days, probably we'll I don't like to say more, get tired and wary and more mistakes you make and stuff like that. Computer hopefully doesn't make a mistake. But in this time and age, and now I haven't said anything about, these are at the values of these, say, let's just look at C and phi, because these are their scientific values. What if there's a natural variation in C and phi that I don't know? So then I have to do a probabilistic simulation with sample and pick combinations of C and phi, and redo this. So I can easily have billions of calculations for probabilistic simulation. So it's going to be quite a few summers that will be back. Old man coming back. I got it. Okay, joking aside, this is not something that you do on a piece of paper. Still, computer is going to give you a bunch of values at each of these sites, each of these locations, and I'm just showing you the results from a program that does slope stability analysis. It plots up a contour plot, right? Each of these colors represent a certain range of values, and the cold values have higher factors of safety, and the hotter values towards red, they have the lower factors of safety. So within this contour map, the lowest one was here, and the corresponding failure surface was that. So you see, for a simple homogeneous slope, there is no slope height times something distance, there is no splitting angles. Generally, it is a function of the slope angle and a height some combination, but almost all of them go to the top. Okay? But the program does it. And this is, again, I need to iterate that this is a theory course, of an infinite space in quite a few dimensions, 1, 2, 3 dimensions, x, y, and r, 3 dimensions, infinite space, I'm picking only 100, 100, 100, which is, very coarse.
But that method was developed in the 70s, right? Like Bishop's. How did they do it at the time? How did they manage to evaluate the credible range of values?
They guessed. At that point, like I said, many graduates of civil engineering programs found a job, and day after day they did nothing for weeks, months, years till they quit, died, whatever. They did only slope stability analysis, and it took a team of say 6 whatever people to work on a project, starting with different assumptions and crank through it and that kind of stuff. And even then they based a lot of what's critical, a lot of it was based on gut feeling and experience and know-how and black magic and whatever else. And now all that's taken away. But like I mentioned, limit equilibrium was the method for the previous century. In this century, even limit equilibrium has so many problems that the finite element method is taking over, really giving an insight into the material behavior on a local scale, that's how we're going to conclude the course. So still, that's sort of the research and all that. It hasn't really percolated down to consulting offices that much. So I said at the time, I think it's a 60-40 or 70-30 split when it comes to practical slope stability analysis in a consulting office. 70% limit equilibrium, 30% finite elements. But I'm going through all this silly little exercise for you to really appreciate that behind the scenes when you click on a button, what's going on that you would spend probably years calculating. Okay? So that would be the grid search. And I talked about it, that you can look at now the same search for a global minimum from a different perspective. I can find a minimum of a function of 3 variables, x, y, and r, optimize finding the minimum in this 3-dimensional space using many of the mathematical methods that have a much sort of better convergence. Simplex method, Rosenbrock, and a bunch of other ones. But this, it's applied to the problem. The method itself knows nothing about soil mechanics. You're just finding a minima of a function. And I drew this that, in this 3-dimensional space, that generally there could be like multiple minima. Like this is the global minimum, but all these are minima of a function. You want that one. So in the sort of brute force grid search, I pick a bunch of values on a grid, I pick a bunch of radii, I calculate it at all of them, and then I judge it based on the contour map. These optimization methods, they actually converge, they can zero or hone in to the global minimum and find it for you. Much faster, perhaps, than this. But if it's 1 second or a half a second, this time and age, who cares? Right? Back in the days when computers were, slower, it mattered. These days, not that. So the computing power for this type of a problem is there. So we much more care at this point about being able to model the physics. Right? Being able to model what's happening internally with soil mass, as opposed to calculating a bunch of equations based on something fairly simple, if you think of it, a fairly simple method such as statics and undergraduate soil mechanics. Okay, right? You look at it, starting with one big soil mass failing, everybody realized that, hey, what's happening internally to it? then subdivide it into slices and make the slices vertical and realize that, well, it might not be where the critical shear is occurring. Make the slices kind of inclined, make them into wedges. That says much more about the collapse mechanism, but still it's a fairly crude way of looking at it. Whereas if you have a reasonable finite element method, that captures everything for you. But the problem is we will see with finite elements that to set it up and definitely to interpret it is an order of magnitude looking at a map of factor of safety. Right? Finite element doesn't give you okay, this is what the minimum factor of safety is, or what it is. It's giving you something else that you have to sort of artificially look at, like, the strength reduction method we'll talk about later, and of course. But it's not giving you a failure mechanism, or it's giving you a failure mechanism. It's not giving you a failure surface. So, you can't have a free lunch. There's always a trade-off. Something for something. So any thoughts, any questions about finding the minimum factor of safety for a slope without having signs hammered into it saying that this is where the critical failure surface is? So, and you think that this is complicated, right?
Yes.
Well, it ain't. Let's go with the simple assumption of what is it that circular failure methods, is the failure surface circular at all times? Is it a good assumption? For what soils? It was mentioned on a couple of slides. I mentioned a couple of slides ago that circular failure surface is good for when? What kind of soil? Clays. Homogeneous clays, generally they tend to fail under simple circumstances, circular failures. Now, just like it says right there on the first slide. Now, of course, I'll talk about it after covering the non-circular methods, that even finding the failure surface is a fairly complicated affair. But what if there are multiple materials? What if there is pore water pressure? What if there is load on a slope here, on a crest, or at the toe? None of it is added. Then, of course, that adds much more complexity. Pore water pressure alone can be complicated. Loads, whatever, multiple soils, all sorts of things. Anchors, for example, for stabilizing snow, piles, whatever. If you basically, no pun intended, pile up these various things onto it, it always adds a degree of complexity that we haven't even talked about. We'll talk about it later. But let's just investigate the shape of the failure surface. So, circular failure surfaces are good for homogeneous soil, generally clays. So if I have sand, and if I have multiple soils, well, then the failure surface may not be circular. I'm going to draw you the simplest case. Think about it for a moment. Doesn't matter what the material is. What's the shape of the failure surface?
spin.
Would that weak seam with its material properties being much less than that of the surrounding soil, would that influence the shape of the failure surface? Definitely. So, generally, without thinking too much, probably the failure surface would start out as a circular one, then it becomes linear in this weak seam, and when there is enough thrust, it will curve up. So, some kind of a non-circular. Right? So try to now use only circular failure surface methods. Would they find the critical or the minimum factor of safety? Chances are they wouldn't. And what would they do? Even if it's the best, they would be, like a big circle like this, touches it's only a small portion of a circle would be actually within this weak seam if missing it, altogether. If it's a bigger circle, it just only goes through two little areas with weak material. So clearly for these type of a problem, the circular failure surface method will find a minimum, but that minimum is physically not the minimum that I want because the actual mechanism of failure is completely different. Okay, so what I want you to appreciate that you have to use the right kind of hammer for the problem. You have to know what your hammer can do and what your hammer cannot. Or talking about slope stability, the appropriate method. Some methods are good for certain things and they're not good for other things. So you have to look at the problem and of course use the right size hammer that goes with it. Now for non-circular methods, they have no problem with material heterogeneity simply because they can span the boundaries, and this could be looked at as a material heterogeneity, that there is a dissimilar materials and it is preferential for the failure plane to develop in a weak material and run along it. And the last one can capture reverse curvature failure surfaces. So what would be, reverse curvature failure surfaces? Yeah, like that. So if I have a situation like this, again, I'm just making it up as I'm going. But let's say there is a stronger material here, put it stronger, let's put that one as a weaker material. Slope failure. So, slope failure will occur something like this, then it will turn, reverse the curvature, go like this, and turn again. So there are reversals of the curvature. So try to do that with a circular method. You can. It will find some minimum factor of safety. That's the minimum for the circular failure surface method, but that's about it. So that would be a reverse curvature. Now the funny thing with the non-circular failure surface methods, that if indeed the critical failure surface is the shape of a circle, a non-circular method can adapt itself and find it. Right? So again, this is what I've sort of mentioned to you, that the key with these non-circular failure methods, that it is purely now an optimization problem of the mathematical sense. We're optimizing the shape of the failure surface in an n-dimensional space. So if the situation is something like this, that I'm just going to draw you the true failure surface, looks something like that, and I start up with a sort of non-circular failure surface method. I'm just going to subdivide it into three I get slices, blocks, wedges, whatever you want to call them, and each of these points have sort of 2 degrees of freedom that they can move, and they can sort of, these ones are constrained to the slope, but these can move along anywhere. So then I'm optimizing this 2, 4, 6, 8 minus 2 because of a constraint. So a 6-dimensional space. So these will, I calculate a factor of safety, then these get moved along, and these will eventually converge to the circular shape, if that's the critical one. So we can say that a non-circular failure surface method can always be used as a circular failure surface method because it can take up its shape, the circle. But the other way around doesn't work. A circular can be always a circle. It cannot be a non-circle. You good with this? So it has definitely many advantages over circular methods, right? If it's sort of this optimization built in, it can find a circular one if that's the case. Now, why wouldn't anybody just run out and use non-circulars as opposed to circulars? You know, there's always a catch. There's always something. So what would be the problem? Anybody can guess? You know, one of those things that you know it's coming. Well, of course, they're much more complicated. Both their derivation, as we will kind of see for a few minutes today, and also finding, I mean, if you think of it, there is no really a brute force approach. Well, I show you one, but you can't really generalize it. Like for the circular one, the center of the circle and the radius. We set up a grid. At each grid point, we calculated the factor of safety for a bunch of circles, and that's it. For here, for non-circulars, there is no circle. It's defined by a bunch of points that are basically line segments or higher order curves. So each of these has a location. So sometimes what they do is that they set up grid points at each of the points that define, well, it's actually this goes over this way, or rather it only goes along the line, and also this one can only go along the surface. Everybody sees it as these start and end points can only move along the slope surface. It's kind of a constraint. Always have to be on the surface. Everybody sees that. Whereas these other interior points, they can be pretty much anywhere. So they can set up a brute force approach that, let's move this point here, and let's move that point there, and let's leave these two for the time being. So we end up with some kind of weird looking calculator factor of safety. Now let's move this point there, let's move that point here, make another one. So it gets pretty complicated because now it's multiplicative, right? For every grid, there are multiple grids, right? So for every combination, so if say this is a coarsely a 10 by 10, and this is a 10 by 10, and this is a very simple, so there would be 100 points here, but for each of those 100 points we are locating, the other point can be another 100 locations, right? So that would be 100 times 100. Right, so this 100 points, another 100 points. So, that's already a big number. Plus the surfaces, but this is only what the 1, 2, 3 wedge situation. Generally, they have 20, 30 wedges. So again, it's a huge number to calculate factors of safety. Or another way would be to resort back to this sort of mathematical approach to optimize an n-dimensional space where each of these xy locations of each of these points on a failure surface are degrees of freedom. So, yes, it is a much better method when it comes to what it can do, and yes, it is a much more complicated method. So, going back to if I give you a non-circular one for midterm to find the factor of safety, I don't expect to see you probably ever. You'll be getting tired of it and never come back. Okay, so it's an involved procedure. Now let's see the one that it was derived much later than some of the other ones, but this is a unifying one, so I put a lot of emphasis on it. It's called the GLE, Generalized Limit Equilibrium. So using this procedure, making certain little assumptions, you can derive other methods from it. Even you can derive from this one Bishop simplified and a bunch of other ones. So that's why it's called the generalized limit equilibrium or GLE. Good thing about it that based on little assumptions and the shape of a failure surface, it's the same for both circular and non-circular. Overall moment and overall force equilibrium is considered separately, but it's maintained. So remember those 6 equations, 3, 4. So all 3 overall ones, global ones, are satisfied. And some of them, as we will see, are satisfied locally per block or slice or wedge. And there are different assumptions about the interslice forces, and based on the assumption of interslice forces, you can derive all the previous methods from it. That's why it's generalized. Okay? So let's just look at it. The general setup. So if I ask you the question, what makes this a non-circular failure surface? And then you're going to tell me one letter of an alphabet. Look at the figure and tell me what makes this, or rather, if this would be a circular failure surface method, then what letter of the alphabet would be equal to 0? Quick midterm question. 2-liner or 1-liner. Or, give me one letter. Rather, how many letters in the alphabet? 26, maybe, whatever. Only 10 of them are living here, so you got a 1 in a 10 chance to guess. Of course, it's not enough to guess. I need some evidence that you know what you do. So give me one letter of the alphabet. So let's put some tally on things. I heard some rumors of an F. Is that true?
What?
I heard an F.
Yeah.
Okay. An F. Anybody else? L or which one? This one here? And that's L. Okay, I heard an L. We have F and L. Any other letters of the alphabet? Shall I go one by one and sort of explore the space of solutions in a class brute force approach? So what could it be? Anybody else? X.
That's why the question again.
Yeah, knowing the question is really important to answer. So the question was, in this figure, what makes this into a non-circular failure surface method? Or another way to pose the question, what letter should be equal to 0 to make it into a circular failure surface method? F and A. Where's A here?
There are two A's, I think. One on the top and one in the
So
bottom.
this is alpha, this is A. Okay, so we want F and alpha or F and A? F and A. I'm just going to add A.
If you use a frictional velocity, you can come up with a circular surface.
Can you? But then, would it be a method of slices or no? Okay. Torturing you guys. So let's before revealing, let's go back to this one. Refresh.
The line, the radius was by the circle.
Yep. So, if F, and in a way A, but mainly F, if F equals 0, that means that all of these going through the origin, which means all of them lie in a circle, which means that the failure surface is a circle, right? There is no eccentricity within a line of action of the line of action of this line that is perpendicular to the base, right? So all the bases are perpendicular to the center. Okay? So I can use this figure to have, and that's why it makes this statement, same formulation for both circular and non-circular. If I have F equals 0, that means all these resultants or all these lines of action to the base of the slice go to one point, and by geometry, by definition, that means that it's a circle. Everybody sees that? So that's the beauty of this. It's a general kind of generic derivation that, you know, if F is 0, then all of them go to the center and it's a circle. If it's not, then F varies based on a slice. So probably if portion like this, F would be a fairly small number because all of these are kind of on a circle, and same here. But there it's pretty flat here, so F would be a different number. It was a good one, wasn't it? This sort of demonstrates me that you have a good understanding of the nuts and bolts of the derivation. Because, you know, I can ask you to derive something, some situation that is not on a slide, say add the line load on a surface or a distributed load or whatever, that you have to incorporate into the equations. And you know, you have to understand how these things are put together and what each one means. So, for that particular slice, again, note that the equations, particularly this equation, is exactly the same, no matter what the method. We assume for the base of the slice, this is the shear capacity, shear strength, divided by the factor of safety to get the mobilized one. I resolve into two forces, the normal stress times the base area, L times 1 meter, the shear force, which is the shear strength or stress, depending which way you want, times the base area, 1 meter thickness, and I now put this and this into that equation, and I come up with a shear force equation, which is the mobilized shear force. So this is fundamental to all of it. Now, those of you who are taking soil behavior, you know that there are other soil models beyond Lord Coulomb. So what would be, can anybody, who's taking soil behavior? I know at least 3, 4, 5, 6, excellent. So, name another soil model.
The Can-Clay model.
Can-Clay models. Good. What else? You know, Dr. Prager would come to mind for sort of sands, all the strain hardening, softening models, whatever. It doesn't really matter. So now you even see more of a limitation of the limit equilibrium methods. But all of them, one by one, they all are based on a more Coulomb shear strength. Yet more Coulomb is pretty much like, the grade school method when it comes to soil constitutive models. So, just gives you an appreciation. For the rest of you not taking soil behavior and never wanting to take soil behavior, just erase the last 2 minutes from your mind. This is what you need to know. Soil is more Coulomb than the standard. Okay? So, the first statement is resolved vertically for that particular slice. So again, let me ask the same silly question I asked earlier. What does that mean? Resolved vertically, having an equality sign. No. Are there any moments? Resolved vertically, forces on the left equal forces on the right. So what kind of forces are in equilibrium? Yeah, the vertical forces, sum of Fy on that slice are in equilibrium. That's a statement inherent to the derivation of the method. And we have very similar to what we had before for, say, Bishop simplified, where he said that xr minus xl is equal to 0, and here we do not say that. We keep it. And then we go through the same kind of stuff. So this equation is pretty much the same as Bishop simplified, but it has the interslice shear forces. They are not 0 anymore. Now, if I resolve horizontally and have this equality, then which equation is satisfied? Fast. A little bit faster than that. Yeah, some of the forces in the x direction are equal to 0 for the slice. So now it has 2. Both force conditions are equilibrium out of the 6 that we had, local and global. And if I do that, these are the horizontal forces. Again, I leave it for you as an exercise. If you do not believe me, that if you sum all the horizontal forces, it's the E left, E R, all right, and then components of T and P, W is equal to 0 because it's vertical, you end up with this equation. And if you solve for the interslice normal forces on a boundary, you end up with that one. Next statement is the overall moment equilibrium about point O is satisfied. So this is now not a local equilibrium, but a global equilibrium. So now this is 3 equations out of the 6 satisfied. 2 local, first slice, 1 global. So if we, the same idea, W times D, and go back to the figure, W times, and again, he says D, which should be this A here. There is a little bit of screw up in the, between the figure and my, which is, I took it from the book. So this A should be a D, right? It's W times its moment R, which is this, right? So W times D is equal to T times R plus P times sum of P times F. So it would be T, which is always at the base, and a radius is whatever that one, and we have the P, which is the line of action is this, and now it has this eccentricity of F. So this is now in its most generic form, and if we substitute everything, again, I'm not worried about the, the math of the derivations, I end up with this form. And this would be the overall moment equilibrium force. So if I have now, going back to circular failure surfaces, as we established, that the letter of alphabet that should be 0 on that figure is F. If F equals 0, then D or A rather is R sine theta or R sine alpha, and R is now constant, right? It's not changing because the base angle is not changing per slice. It's always the same. It's a circle, right? And then we have a much more simplified factor of safety equation. Now, it also says that so this is a factor of safety for overall moment equilibrium. Now the method goes even further and it says that what if overall force equilibrium is satisfied as well? That means if there is no surface loading, which means that there is no load on a slope, that means if I add up all the ERs and I subtract the sum of the ELs, there is no unbalanced normal to the boundary, interslice boundary force, and the sum of the interslice shear forces are equal to 0 as well. Right? It says that if I put everything together in a slope, all of these slices, there is no net difference between the e's and there is no net difference between the x's. Overall force equilibrium. So, does this satisfy how many conditions of overall force equilibrium in one statement? 1, 2, 3. No, there are no 3, right? Only 2. So, 1 or both. It satisfies both, right? This would be in the x direction, that would be in the y direction. So now this satisfies local vertical force, local horizontal force, overall moment, overall force, horizontal and vertical. So the only thing it's not satisfying is a local moment equilibrium. Okay? That's not satisfied, it doesn't say. So, if I say that this is equal to 0, right, it's an equilibrium, then this has to be equal to that, so the difference is 0. And these are now all the horizontal forces. So we have the sum of P times sine alpha, which if you look at the figure, P times sine alpha, so that would be a horizontal force. Sum of those across the slices, minus the one that's opposing it. These are, if you recognize, what capital letter is this? From here to there. Give me one letter of the alphabet. Capital T. Exactly. So that has to be met by capital T's, and if you don't believe me, well, the same form with some substitutions. Again, T times cos alpha because we're resolving it in a horizontal component. So this says, this expanded equation says that the forces in the horizontal direction externally, like the whole slope, has to be in equilibrium. There are no vertical forces as such. So from that one, I have another equation for a factor of safety, but this time for forces. So I have now, funny thing, I have two equations for factor of safety, one for moments and one for forces. So the procedure is that in order to solve for the factors of safety, P must be known, right? And in order to calculate P, I need to know XR and XL. All I'm saying here, big student question after the lecture is, but I said they're zero. Their sum is zero. Or rather, the sum of their differences is zero. They're individually not zero. The sum of their differences is zero. So I don't really know what XR and XL is. And if I make the following statements, substitutions, then each method can be derived from the GLE. If I say XR minus XL is zero, that's what Bishop said. If I put that into the equation, you retrieve Bishop's equation. If you say that X over E is equals to constant, which means, if you look at it, I'm just going to draw 3 slices. It means that the orientation of them is always constant. If this is E and that's vertical is X, their ratio is always the same, which is the orientation of the interslice forces, and I can illustrate it to you. It's a pretty bad assumption. Let me draw you for a bunch of slices. I say that X over E is equal to 1, which means that all of them are oriented at 45 degrees. These are the interslice forces. So the typical final exam question is, circle the interslice forces that you think they're incorrect. And then you break out your pen and you circle the couple of things. So the question is, which interslice forces, the way they are oriented, are not that good? First, you need to know what interslice forces are. These are the forces that are applied, one slice applied to the other slice. Well, you can't have or. But depending on what I think. Let's stick with left and right. So you want to circle the left 2. Anybody else wants to circle something else?
I agree with her.
You're excellent. Anybody else wants to circle something else? Well, I guess I have to agree with her too. Right? Ideally, these are forces applied between slices. So if this is pushing down on that one, this is coming down, it's pushing it down, then these should be going basically upwards, right? These are getting pushed up and out, right? It's fading. They can't drive further into the slope. But Spencer says for whatever reason that their ratio is constant. So it may not be the best assumption. Or for some special cases. And the last one, the Morgenstern price, it says that the ratio of the shear to the normal is some function. And the sum function is basically that the ratio is constant. So this is, if you will, it's pretty much like what Spencer said. Or it goes from left to right as a curve, a sine, or a trapezoidal, or some, well-defined function. So tell me, out of these 4, which one would be a good and why, based on our discussion. Or put it that way, which one of those curves would represent the following, what she suggested? Remember, it's giving you from left to right the angle, which is basically, I give you here, the angle is the angle that's made between, I guess, E and L, the interslice force inclination. That's what the figure is.
So it's all right.
Yeah, so we can safely say that if you kind of look at the kind of the curve of this, that this is some kind of a sine. Now, if I have a long, drawn-out failure surface, something like this, then it would be, done this way. But everybody agrees that it has some kind of a, it goes up and peaks and comes down, or goes up, stays kind of constant and comes down. So using the right one for this Morgenstern-Price method is pretty much up to you as the analyst to pick the appropriate one. But what I'm trying to illustrate here is that you go to make an assumption about the inclination of the interslice forces, and basically you pick a method. Okay? So probably this is a good point. Stop for the week and we'll continue.